All right, guys, so welcome back to part 2. So there's a cute little proof in the textbook if you guys are interested in the textbook. Normally we would prove it in class, but just given the circumstances, let's just focus on the applications because I think that's more important given our very, very special circumstance. So let's look at more examples. Okay, so the instructions for all of these, so we'll do some together and then you guys can push pause and try it on your own, would be to find the derivative. All right, so here's the first one we'll do together. So we have that f of x equals 1 over x squared, okay? And we're going to find the derivative using our shortcut, so we're not going to use the definition of the limit, or definition using the limit. So we have a rule for a constant, for x, and for x to the n. Right? And now, right now, 1 over x squared doesn't look like any of that. So we can be clever, and we can make 1 over x squared look like x to the n. When we have x to the nth in the denominator, that's like a negative exponent. So I'm going to change 1 over x squared to x to the negative 2. All right, and now that we have that, then we can say, all right, I'll go back to prime notation, that f prime of x is equal to, and we can use our power rule. So we can bring down the exponent, and for the new exponent, we subtract 1. All right, and you can leave it like that. I'm fine with that. Or, whoops, let me erase that. Or we can write it without a negative exponent. So since the negative exponent is on the x, we can move the x cubed down to the denominator. All right, so we could do something like that. Another example where we have to do a little bit of clever manipulation is with root functions. So like, for instance, the square root of x. That doesn't look like x to the n. But remember, square roots and roots are just exponents. So with the square root, our index is 2. We don't see it. So we can change that to an exponential form by looking at x to the 1/2. So a little side note, thought bubble. So from your pre-calc, remember the nth root of x is just x to the 1 over n. All right, so we had that from pre-calculus. Also, I mean, let's write it since we're here. 1 divided by x to the n is x to the negative n. All right, so those are the two properties we used. Okay, so now that we have that, we can find the derivative. So we can just write g prime of x, or if you're feeling fancy, that's the same as dg dx, or you can write d dx of the square root of x. All of these are equivalent. Those are all equivalent expressions. But no matter how you write it, how you notate it, it's the same one. We're going to bring the exponent down and then subtract 1 from the exponent. So 1/2 minus 1 is negative 1/2. Okay? All right, let's get rid of the negative exponent. Let's clean it up a little bit. So negative exponents in the top means we're going to send it downstairs. So like that, and then make the exponent positive. And then instead of writing x to the 1/2, why don't we give them what they originally gave us? And they wrote everything in root notation. So we can do that too. Okay, so there you go. So those are some great solid examples. Let's have you guys do a couple. So I'm going to write out how many examples? A handful of examples. And then go ahead and push pause. And we'll see how you guys do. So for all of these examples, the instructions would be the same. It'd be find the derivative. All right, so welcome back. So let's see how you guys did. Number 3 is just a direct application of the power rule. It just has a variable a instead of x, but that's okay. No big deal. So rules are the same. You bring down the exponent, and then you subtract 1. And that's that. For number 4, I would change this to an exponential form. So we still have the x cubed, right? And now the 4, since that's the index of the root, that's going to become the denominator. So something like that. So when you take the derivative, you bring down the exponent and subtract 1. So 3/4 minus 4, 3/4 minus 1 is negative 1/4. You can leave it like that. You can also try to get rid of the negative exponent. So 3 stays on the top, 4 goes downstairs, and then we have x to the 1/4, now with a positive exponent. And then you can even take it a step further, and you can write x to the 1/4 in the root notation. So like that. All right. G of x equals 1 over x cubed. You guys rewrote that as x to the negative 3. So now the derivative, and make sure you write out the derivative. Don't just say, you know, for instance, that a to the 9th equals 9 times a to the 8th, because it's not, right? You want to make sure you're putting in the operation and you're taking the derivative. Any hoot, bring down the exponent, subtract 1 for the new exponent. You can write it like that. You can rewrite it without the negative exponent. So we have a negative that will stay out front. 3 stays on the top. The negative exponent is just attached to the x, so that's going downstairs. So the answer is negative 3 over x to the 4th. Right, finally, number 6, we didn't do an example like this. But let's see if you guys are able to critically think your way through this one. Our strategy is to turn roots into exponents. So that's a great first step. And now we have an exponent rule. When we have the same base and we're multiplying, what do we do with the exponents? We add them up. All right, so what's 1 plus a half? 3 halves. Wait, there we go. All right, so h of t equals t to the 3 halves. So now we're ready to take the derivative. So we bring down the exponent and subtract 1 for the new exponent. Okay, and we can clean this up. There's lots of ways to write this. You can write it, remember t to the 1/2 is like the square root of t. You can write it like that. You can put everyone that's upstairs in the numerator, like that. Either one, that's good. Okay, and then just to do a little thought bubble, this step right here was just an exponent rule. If we have the same base and we're multiplying, we can just add up the exponents. So that's one of your exponent rules from algebra. Okay, so good. So that's our power rule. We're going to learn a lot of other rules right now. And they all are followed, or they can all be proven, and they all come from the limit laws. Because remember, a derivative is just a limit. So using everything we know about limit laws, we have the following theorem. All right, and again, remember, it follows from the limit laws. So if you wanted to prove any of these, you would just go back to the limit definition of the derivative, plug everything in, and simplify. And then we get all of these wonderful properties. Okay, the first one is if we take the derivative of a constant times a function, okay, we can just pull that constant out and then focus on the derivative of just the function. Okay, remember you can write it using Leibniz notation, or you can use prime notation too. So it's saying the same thing. Okay, let's do the next one. If we have the sum of two functions and we want to take the derivative, guess what we can do? We can take the derivative of each function and add them up after. And if it works for addition, it must work for subtraction. That's better. So we have this property. So we can take the derivative of the difference. Okay, and then, whoops, that's about, oh, and how do I get rid of that? All we have right now. We have multiplication and division limit laws, but they do not apply here. So I'm going to write just a little warning. The derivative of a quotient, we are not allowed to take the derivative of the top divided by the derivative of the bottom. It's much more complicated, unfortunately. Okay, and then likewise, if we were taking the product, we're not allowed to take the derivatives of each function and then multiply them. Okay, so that's that. So don't do those. We'll learn rules for the quotient and the product soon enough. All right, so let's do some practice. Let's practice finding some derivatives. So let's define f of x as 5x squared plus 3x to the negative 2 plus 7. Oops. Plus 7. Okay, so if you want to, so again, we want to find the derivative. So I'm just going to rewrite it like this. All right, and we see that we can use a lot of the theorems that we just had. So we have a sum, so we can take the derivative of all three terms separately. And then we have a constant in front of our power function. So we can ignore the constant a little bit and just focus on taking the derivative of the x squared and the x to the negative 2. So again, what we can do is we can move the constant in front of the derivative of our power function and take the derivative of all three terms, okay? So this is what the laws we just said, or we just laid out. All right, so the constant law and the addition law says we're allowed to do this. Okay, so we know how to take these two derivatives. We know how to take these three derivatives. So the derivative of x squared is the power function. So move the exponent in front. New exponent is 2 minus 1. All right, next up, x to the negative 2 to take that derivative, move the exponent down, subtract 1. And finally, do you remember what the derivative of a constant is? That was the very first thing we showed. 0. Okay, so what's our final derivative? So f prime of x, let's clean it up. 5 times 2 is 10. And then 3 times negative 2 is negative 6. And then x to the negative 3. And you can just leave that negative sign there. I'm fine with that. Okay, so excellent. So let's look at some examples from your homework set. We are going to section 3.1. That's where we are. And we're doing number 58. Okay, so let's open up that textbook. And we are on page 181. We're going to find an equation of the tangent line to the curve y equals x to the fourth plus 1 that is parallel to the line of 32x minus y equals 15. So this is exciting. So let's write down some things. We're going to find an equation of the tangent line to this curve, x to the fourth plus 1, and we want the tangent line to be parallel to the line 32x minus y equals 15. Okay, so let's kind of get a picture of what's going on. Very visual problem. X to the fourth kind of looks like a parabola, and then the plus 1 means we're just going to be vertically shifted 1 unit. All right, so that's x to the fourth plus 1. 32x minus y equals 15. I like to put things in slope-intercept when I'm trying to graph. So I'm going to bring the y over to the other side. I'm going to bring the 15 over. So just rearranging terms. So y-intercept is negative 15 in a very steep slope, right? So maybe something like that, for instance. All right, an approximation, right? So what we're going to do is we have to find the equation of the tangent line that's parallel to this line. So taking this line, we have to find where, I don't know, maybe right there. The rate of change is going to be the same right there. Okay, and I just kind of eyeballed it. So we want to find the equation of that line. Let me highlight it. We want to find the equation of this line. Remember, when we want to find an equation, we need a slope and we need a point. Okay, so we can get our slope from there, right? And then it'll be our job to find the point after that, okay? So what is the slope in this case? Y equals, remember, mx plus b. So your slope in this case is 32, so that's half the battle. So remember, going back to this thing, this curve, x to the fourth plus 1, now we know that the slope of the tangent line is 32. Well, what tells us the slope of the tangent line? The derivative, f prime of x, is the slope of the tangent line. And since it has to be parallel, since the slope of the tangent line has to be parallel to y equals 32x minus 15, remember, parallel lines have the same slope. Parallel lines have the same slope. So the slope of our new tangent line has to be m equals 32. So this question, how we're going to figure out where that is, we have to figure out where the derivative is equal to 32. Oopsies. So where is the derivative equal to 32? So that's the question. And if we can answer that, we can write the equation of the line. Okay, so what is y prime? All right, so remember, it's the derivative of x to the fourth plus 1. Well, x to the fourth plus 1, we have to take the derivative of first x to the fourth. And then what's the derivative of a constant? It's 0. So the derivative is 4x cubed. And now we want to know where 4x cubed is equal to 32. And that will tell us the point on our x to the fourth plus 1 where the tangent, the slope of the tangent is 31. Let's solve this. Divide both sides by 4. 2 to the third is 8. So that's going to be, oh, I just gave it away. 2 to the third is equal to 8. So that means x equals 2. X equals 2. So that means, let's go back up to our drawing. That means this point right here happens at when x is equal to 2. Okay, and so if x is equal to 2, what's going to be the y value? All right, 2 to the fourth is 16. 16 plus 1 is 17. So the ordered pair is 217, okay? Woo! That was a long process. So what do we have now? We have a slope, it's 32, and now we have a point, 217. So now we get to write the equation of the line. All right, so again, slope is 32, and our point is 217. So y minus 17 equals 32 times x minus 2. All right, solve this for y. Distribute that 32. All right, and then you add your 17 to both sides. All right, so let's take a quick break and we'll continue the rest of the section in part 3.